Okay, so get ready, right? Because we're about to dive deep, really deep into particle physics.
Yeah.
We're talking about the Large Hadron Collider.
The LHC.
That thing,
Yeah.
the quest for new particles.
Absolutely.
And all of the really ingenious ways that physicists are trying to find them.
It's incredible, right?
Yeah, it really is. It's like detective work.
It is.
But on a subatomic level.
Yeah, totally.
So it's really, really cool that we're diving into this paper.
What's really cool is that we're taking excerpts from an actual physics paper
Oh, okay.
called Simplified Models for LHC New Physics Searches,
Oh, wow.
which sounds very complicated, but we're going to break it down.
Yeah.
Don't worry.
Okay, good. Because I was going to say, I'm all about making the complex a little less complex. So let's start talking about these simplified models.
Yeah.
Because that's kind of what stood out to me.
Sure.
Can you just give me, like, I don't know, an analogy or something that'll help me wrap my head around what it is we're talking about here?
Yeah. So, I mean, a simplified model is basically, instead of trying to think of every single possible new physics scenario,
Right.
you kind of pick a direction
Yeah.
and go for it.
Okay.
So it's like using a metal detector instead of digging up your whole backyard.
Okay.
If you're looking for treasure.
Right. So we're being very, very specific here.
Exactly. Yeah.
And we're trying to be specific because the standard model of particle physics, as wonderful as it is, still has some holes in it.
Right. It does.
And so we were looking to fill those holes.
Yeah.
What are the holes? Just remind me.
So the biggest holes are things like, we don't understand what dark matter is.
Right.
We don't understand why there's more matter than antimatter in the universe.
Okay.
Things like that.
Okay, so these are some pretty big questions.
Yeah.
And so that's where the Large Hadron Collider comes into play, right?
Exactly.
We're smashing these protons together
Right.
at these insanely high speeds, trying to just blast new particles into existence.
Right. Yeah. You're creating so much energy in such a small space
Yeah.
that you're basically hoping that some of that energy
Yeah.
can be converted into mass.
Right. And that mass will be these new particles.
Exactly.
Okay. So then how do these simplified models come into play? Like, how do those help us?
So you have all this energy, right? And it's creating all these particles. And then those particles are decaying.
Yeah.
So you have just this enormous amount of data
Yeah.
from all these collisions. And the simplified models are a way to kind of like sift through that data.
This is making the problem a little bit more manageable.
Exactly.
Okay.
Yeah.
So instead of looking at all this data and going,
Right, yeah.
it's like, okay, this is what we're looking for.
Yeah, you're focusing on a particular signature
Right. Yeah.
that would tell you that something new is there.
Okay. I like that.
Yeah.
So one of the examples that the paper gave, and I thought this was really fascinating, was this search for a hypothetical particle called a gluino.
Yes.
Tell me about the gluino. What is that?
Okay, so a gluino,
It sounds cute, by the way.
I know.
That does not sound like a scary particle.
Yeah. No, it does.
Like a gluino.
Yeah.
Okay, tell me.
It's predicted by a theory called supersymmetry,
Okay.
which basically says that for every particle we know of,
Right.
there should be a partner particle that's like a little bit heavier.
Okay.
So the gluino would be the partner of the gluon,
Gotcha.
which is the particle that carries the strong force.
Okay, so it would be a pretty big deal if we actually found this gluino.
It would be huge.
Right. That would be amazing.
Yeah, it would be a really big deal for supersymmetry.
Okay, so how in the world do we even begin to look for it?
Right, so that's where the simplified model comes in, right?
Okay.
So the simplified model is basically exploring the different ways
Yeah.
that this gluino could decay.
Okay.
And it would leave behind certain particles
Yeah.
based on how it decays.
So, like, depending on how it decays, it leaves behind a different signature.
Exactly.
Yeah.
Yeah, so you can think about it like if you have getaway car, right?
Okay.
And it's leaving tire tracks,
Yeah.
depending on which route they take.
Okay.
They're going to leave different tracks.
Yeah. Yeah. Okay. That makes sense.
So that's kind of what we're looking for at this simplified model.
So we're like these detectives looking at these signatures, trying to figure out what happened.
Yes.
Okay. So what's an example of a signature then? Like, how could the gluino decay? What would we see?
Okay, so one way is we call it like a direct decay.
Okay.
So you could have a gluino,
Yeah.
and it could decay directly into a quark, an antiquark, and then something called a neutralino.
A neutral winner?
Neutralino. Okay.
It's another hypothetical particle
Okay.
predicted by supersymmetry.
Okay. We have a lot of hypotheticals here.
We do. We do.
Okay, so what is a neutralino?
So a neutralino, interacts very weakly
Okay.
with other particles.
Okay.
And in fact, it could be the dark matter particle.
Whoa, hold on.
Yeah.
So we could find the Gluino,
Essentially.
and that could lead us to dark matter.
It could, yeah.
Okay, cool. This is blowing my mind a little bit.
Yeah, it's pretty cool.
Okay.
It's very exciting stuff.
All right, so that's one way that it could decay.
Yeah.
What's another way?
Another way would be through what we call a cascade decay.
A cascade decay. What's that?
Yeah, so that's basically where the gluino would decay
Okay.
into other particles, like maybe a chargino.
Which is another hypothetical particle.
Right.
And then that would decay into something else, and then that would decay into something else.
So it's like this whole chain reaction.
Exactly.
Right.
Yeah, like dominoes.
And
then you might end up with a neutralino at the end of that.
Okay, so we could still end up with that neutralino.
Yeah.
Which could be dark matter.
Yeah, exactly.
Okay, all right. So we have these different ways that these gluinos can decay.
Right.
But then, so we see them in the Large Hadron Collider.
So we don't see the gluinos directly.
Okay.
What we see are the particles that they decay into.
Okay.
So what we do is we look at the energy and momentum of those particles.
Okay.
And we see if there's any like missing energy or momentum.
Okay.
That could be a sign of a neutralino, which we wouldn't be able to detect directly.
Okay.
Because it interacts so weakly.
So we're looking for clues, basically.
Exactly.
We're looking for like a specific energy fingerprint almost.
Yeah.
That would tell us, okay, this is how the gluino decayed.
Exactly.
And it might have produced a neutralino, which could be dark matter.
Yeah.
This is amazing.
That's really cool.
Okay, so it's not just about smashing the particles together.
Yeah.
We need these models to guide us.
Yeah. You have to know what you're looking for in the data.
Okay.
Because otherwise it's just like a giant mess.
Yeah, I was going to say, otherwise it's just this big mess of particles.
Right. Exactly. Okay. This is fascinating.
And this paper, I mean, this is just one example.
Okay.
They go on to talk about, they have this whole catalog.
Of all these different simplified models.
Okay, so they're looking for other things besides just gluinos.
Right. They're looking for all sorts of different new physics scenarios.
Okay, so tell me, what else are they looking for?
So, for example, they talk about what we call multi-jet events.
Multi-jet events.
Yeah.
Okay, tell me more about that.
Yeah, so multi-jet events are basically when you have a collision and it creates multiple jets of particles.
Okay, and jets are just like, what, showers of particles?
Yeah, exactly.
Okay.
They're collimated sprays of particles.
Okay.
That come from, quarks or gluons.
Okay, so we see these multi-jet events, and what does that tell us?
So these jets can be a sign of particles that we haven't directly observed yet.
Okay.
Because, some of these particles might decay very quickly into other particles.
Yeah.
And those particles will then create these jets.
So it's like a trail of breadcrumbs.
Exactly.
Okay.
And the paper specifically talks about searching for multi-jet events that don't have any missing energy associated with them.
Okay, so no missing energy. What does that mean?
So missing energy usually implies that there's some particle that we didn't detect.
Right, like those neutralinos we were talking about.
Exactly.
Okay.
So if we're looking for multi-jet events with no missing energy, it means we're looking for scenarios where all the particles that are produced are ones that we can actually see in the detector.
Okay, so it narrows down the possibilities.
Exactly, yeah.
Okay, so what are some of those scenarios then? What could create these multi-jet events without any missing energy?
Okay, so one really interesting possibility is what's called an anomalous three-gluon coupling.
Okay, anomalous meaning?
Anomalous meaning like unusual, not what we would expect.
Not what we would expect based on the standard model.
Exactly.
Yeah.
So in the standard model, gluons, which are the particles that mediate the strong force, they can interact with each other, but they do so in a very specific way.
Okay.
But what if there's some new physics, some new particle or some new force that changes how these gluons interact?
Okay.
So that's what an anomalous coupling would be.
So it would be like a deviation from the expected behavior.
Exactly, yeah.
And how would we see that? Like, what would that look like in the detector?
So one possibility is that we would see events where three gluons interact, and they produce a very distinct pattern of three jets. It would be a very specific pattern that's determined by the kinematics, the energies, and the momenta of the gluons.
So we'd be looking for this very specific three-jet signature.
Exactly.
Okay, and if we saw that, that would be a sign of this anomalous coupling.
It could be, yeah.
Okay, and that would point to new physics.
Exactly.
Wow. Okay, so by studying these gluons and how they interact, we could potentially uncover a whole new layer of physics.
Exactly.
That's incredible.
Yeah, it's really cool. And this is just one example of what we could find with these multi-jet events.
Okay, so what else is out there? What other multi-jet scenarios are we considering?
So the paper also talks about multi-jet events that do have missing energy.
Okay, so now we're back to missing energy, which means we could be talking about those neutralinos again.
Exactly.
Okay.
Yeah, so one possibility is that these multi-jet events with missing energy could be a sign of supersymmetric particles called squarks.
Squarks. Okay, remind me, what are squarks again?
Right, so remember how supersymmetry predicts a partner particle for every particle in the standard model?
Yeah.
Well, squarks are the hypothetical partners of quarks.
Okay, so it's like a whole other set of quarks just waiting to be discovered.
Exactly. And these squarks, they could be produced at the LHC.
Okay.
And then they could decay in a way that produces these multi-jet events with missing energy.
Okay, so how would that work? How would a squark decay into jets and missing energy?
So, for example, a squark could decay into a quark and a neutralino.
Okay.
The quark would create a jet, and the neutralino would escape undetected.
So we would see the jet, but we'd be missing some energy.
Exactly.
And that missing energy would be our clue that a squark and maybe even a neutralino was involved.
Exactly.
Wow, it's amazing how these particles, even though we can't see them directly, can leave behind these telltale signs.
Yeah, it's like they're leaving behind clues.
Yeah.
And we're the detectives trying to piece together what happened.
I like that. We're particle detectives. Okay, so we've got squarks, we've got gluinos, we've got these multi-jet events. It's like a whole particle party going on at the LHC.
There really is. It's a very exciting time to be a particle physicist.
It sounds like it. But we've only scratched the surface of what these simplified models can do, right?
Right. Yeah, there's a lot more.
Okay, so what else can these models tell us? What other mysteries are they helping us to unravel?
So one area where these simplified models are really helpful is in understanding some of the most massive particles that we know of.
Okay.
What we call heavy flavors.
Heavy flavors, like what?
So the top quark is a heavy flavor.
Okay.
The bottom quark.
Gotcha.
And there might be even heavier particles out there that we haven't discovered yet.
Okay, so these are like the heavyweights of the particle world.
Exactly.
Okay, and how do simplified models come into play here?
So we can use simplified models to search for new particles that decay into these heavy flavors.
Okay.
For example, let's say there's a heavier cousin of the top quark.
Okay, like a supersized top quark.
Exactly.
Okay.
And let's say this particle is produced at the LHC. Now, this particle is going to be unstable.
Right.
So it's going to decay.
Okay.
And one possibility is that it decays into a top quark and some other particles.
So it's like this heavy particle giving birth to other heavy particles.
Exactly. And those heavy particles might decay into even more particles.
Right, like a cascade.
Exactly.
Yeah.
So you can have these long decay chains
Yeah.
that produce a lot of heavy particles in the final state.
Okay, and those heavy particles would leave behind a very specific signature in the detector.
Exactly. And that's where the simplified models come in.
Right, because they help us to make sense of all those particles and figure out what happened.
Precisely. They give us a way to connect the dots.
Okay, so by studying these heavy flavor events, what can we learn? What are we hoping to find out?
So these heavy flavor events could give us clues about new particles, new forces, even new symmetries of nature.
So it's not just about the particles themselves, it's about what they can tell us about the fundamental laws of physics.
Exactly.
Okay, this is blowing my mind a little bit.
Pretty amazing stuff, yeah.
So we've talked about multi-jet events, we've talked about heavy flavor events. What other kinds of events are we looking at with these simplified models?
Right. So another really interesting category is events with multiple leptons.
Okay, so we're talking about electrons, muons, those kinds of things.
Exactly.
Okay,
Wow.
and what makes these multi-lepton events so interesting?
So like the other events we've discussed, these multi-lepton events can arise in a variety of ways.
Okay.
And each way has its own unique signature.
Right, so we're back to those signatures.
Yeah, exactly.
Okay, so give me an example. What's one way that we could get these multi-lepton events?
Okay, so one possibility is that we have a new particle that's produced in the collision.
Yeah.
And this particle decays into a pair of leptons
Okay.
and some other particles.
Okay, so that would give us our two leptons.
Right.
And what about the other particles? What happens to those?
So those other particles could be anything.
Okay.
They could be quarks, they could be gluons, they could even be other hypothetical particles.
Okay.
The important thing is that they decay in a way that doesn't produce any additional leptons.
Okay, so we're really focusing on those 2 leptons as our signal.
Exactly.
Okay, so what would this look like in the detector? What would we actually see?
So we would see 2 leptons that are very energetic, and they would be close together in the detector.
Okay.
And then we might see some other particles as well.
Yeah.
But those particles would be less energetic.
Okay.
They would be more spread out.
Okay, so it's all about looking for those patterns, those telltale signs.
Exactly.
Okay, so that's one way that we can get these multi-lepton events.
Right.
Are there other ways?
Yeah, there are.
Okay.
So another possibility is that we produce a pair of new particles.
Okay.
And each of those particles decays into 1 lepton and some other particles.
Okay, so we get 2 leptons, 1 from each of the new particles.
Exactly.
And again, the other particles could be anything as long as they don't produce any more leptons.
Right. Exactly.
Okay, so what would distinguish this scenario from the previous one? How would we tell them apart?
So in this scenario, the 2 leptons would be less energetic,
Okay.
and they would be farther apart in the detector.
Okay, so it's subtle differences in the energy and the position of the leptons.
Exactly.
Okay, so what can we learn from these multi-lepton events? What are they telling us about new physics?
So these multi-lepton events are really interesting because they can give us information about the properties of new particles.
Okay.
For example, they can tell us about the mass of the new particle, the way it interacts with other particles,
Right.
and even its spin.
It's spin. Okay, remind me what spin is again?
Right, so spin is a fundamental property of particles.
Okay.
It's a bit like angular momentum,
Okay.
but it's a quantum mechanical property.
Okay, so it's not like the particle is actually spinning.
Right, it's not like that. It's a
Right.
more abstract concept.
Gotcha.
But it's still a very important property because it affects how particles interact with each other.
Okay, so by studying these multi-lepton events,
Oh.
we can learn about the properties of new particles, including their spin.
Exactly.
Wow. Okay, this is amazing. So we've got multi-jet events, heavy flavor events, multi-lepton events. It seems like there are so many different ways that we can search for new physics at the LHC.
There really are. It's like we have all these different tools at our disposal.
Yeah, and each tool gives us a different piece of the puzzle.
Exactly.
Okay, so what other tools are in our toolbox? What other kinds of events are we looking at?
So in addition to the events we've already discussed,
Yep.
the paper also talks about what we call exotic events.
Exotic events. Okay, that sounds intriguing. Tell me more. Oh, exotic events. So these are events that are kind of strange.
Yeah, so they don't fit neatly into the categories that we've been talking about.
Okay.
They might have unusual energy deposition or anomalous timing,
Right.
or they might produce particles that travel a significant distance from the interaction point before they decay.
Okay, so like those champs we were talking about earlier.
Exactly. Champs would be a prime example of an exotic signature.
Okay, and remind me again, why are champs so weird? What makes them stand out?
Right. So champs are charged massive particles.
Okay.
And because they're so massive, they're going to be moving relatively slowly.
Okay.
And that means they're going to deposit a lot of energy as they travel through the detector.
So they're like these lumbering giants, leaving a trail of destruction in their wake.
Exactly. They would stick out like a sore thumb.
Okay, so that's key champies. What other exotic signatures are we on the lookout for?
Another interesting possibility is events with displaced vertices.
Displaced vertices. Okay, break that down for me.
So a vertex is basically the point in the detector where a particle decays.
Okay.
Now, normally, particles decay very quickly. So the vertex is very close to the interaction point where the protons collided.
Okay, that makes sense.
But some particles might live for a little bit longer. And if they travel a significant distance before decaying, then the vertex will be displaced from the interaction point.
So it's like the particle is leaving a delayed signature.
Exactly.
Okay, and why would a particle decay a little bit later? What would cause that?
So there are a few possibilities. One possibility is that the particle is just heavier than we expect, and heavier particles tend to decay more slowly. Another possibility is that the particle is interacting with some new force or new particle that we don't know about yet.
So these displaced vertices, they're like a clue that something really unusual is going on.
Exactly. They could be a sign of new particles, new forces, all sorts of exciting possibilities.
Okay, so we've got champs, displaced vertices. Any other exotic signatures that we should be aware of?
Yeah, so the paper also mentioned something called weird jets.
Weird jets. Okay, you've definitely piqued my interest. What makes a jet weird?
So remember how jets are normally produced by quarks or gluons?
Yeah.
Well, weird jets are jets that are composed primarily of other types of particles like leptons or photons.
So instead of a jet of quarks, it's a jet of electrons or muons.
Exactly.
That is weird. Why would that happen?
That's a great question. And honestly, we don't know for sure. It
Okay.
could be a sign of some very exotic particles
Okay.
or some very unusual interactions between known particles.
So it's like these weird jets are a complete mystery.
Pretty much,
We're
yeah.
just starting to scratch the surface.
Exactly, and that's what makes them so exciting.
Okay, so we've got champas, displaced vertices, weird jets. It sounds like the LHC is a cosmic zoo of particle weirdness.
It really is. And we're just starting to explore all the strange and wonderful creatures that live there.
So where do we go from here? What's the next step in our exploration of this particle zoo?
I think the next step is to keep doing what we're doing, collecting more data, refining our models, and looking for those telltale signatures that will point us towards new physics.
So it's all about the data.
Data is king in particle physics.
And the more data we have, the better equipped we'll be to unravel these mysteries.
Exactly. And who knows what amazing discoveries await us.
Well, I'm excited to find out. This has been an incredible journey into the world of particle physics. And I have to say, those simplified models, they're pretty darn cool.
They really are, and they're helping us to push the boundaries of human knowledge.
So until next time, keep those minds curious. And remember, there's a whole universe of particles out there just waiting to be discovered.